Hello, everyone. We have a treat with us today. We are going to be speaking to Dr. S. Seetha, who is an ISRO veteran. She's now retired, but when she was in the agency, she was a behemoth and she had her hand in nearly all missions to come out of ISRO. Just before retirement, she was the program director of the Space Science Program Office, where she acted as a liaison between science and engineering teams in important missions, including missions like Mangalyaan. Welcome, Dr. Seetha. Thank you so much for being with us today. It's lovely to have you here.
Thank you so much.
Can we start off by talking a little bit about your work in ISRO and your career trajectory there for our audience to have a bit of a context about your work?
I joined ISRO in 1980 after finishing my MSc at IIT Madras. And then we were just beginning with some space science missions at that time. ISRO had already launched the science payloads on Aryabhata and also on Bhaskara. But then when I joined, it was decided that we should have the next set of science experiments on Indian satellites launched by Indian launch vehicles. Whereas Aryabhata and Bhaskara were launched by the Russian launchers. It was decided in around the 80s that with the SLV, ASLV coming up, that it should be launched on small Indian satellites on Indian launchers. So we started working on that. We initiated the work with a proposal at that time for studying gamma ray bursts. If you know, gamma ray bursts are some of the highest energy transient events in the universe. There's an immense amount of energy which is emitted in the highest energy of the electromagnetic spectrum, that is the gamma rays. And at that time, the gamma ray bursts had been discovered, and we were just the analysis was going on as to what these kind of objects could be, which could emit such high energy emissions. And at that time, this was discovered actually serendipitously by satellites which were launched to actually monitor whether the nations were agreeing to the nuclear treaty and that they were not having any nuclear explosions in atmosphere. That was a thing. And so these are the satellites which were monitoring those. They suddenly saw that there was this immense amount of energy and burst coming from the sky. This they triangulated with multiple satellites and found that it is actually coming not from the Earth, but it is indeed coming from far away in the universe. And it was not known how far away it is from and so on. So at that time, the decision was that we should have as many satellites as possible in the sky so that the triangulation can happen all the time. See, these gamma ray bursts can happen anytime and anywhere in the sky. And so we need to cover as much of the sky as possible all the time. So at that time, everybody had smaller satellites, and so internationally, it was decided that we should have as many satellites in the sky so that we can triangulate any gamma ray burst which is observed by any of these satellites. So we needed minimum of 3 satellites to triangulate in each of the hemispheres also. So that was a very topical science topic at that time, and we also had a constraint on our Indian satellites, which could be launched by Indian launch vehicles, that we could have only experiments less than 5 kg. And power was also limited to 10 watts. So this was an experiment which fell very well into that frame of constraint and also the science relevance at that time. So we made this gamma ray burst payload, and it was flown in the SROS series of satellites. Unfortunately for us, the SROS 1 and 2 were failures, the launch were failures. But in the SROS C, it worked, but it had a short life. But then, finally, in the SROS C2 vehicle, the experiment actually performed very well. We could actually be on the international um, arrangement where we were part of the number of satellites which could triangulate multiple bursts, and we discovered. Um, I shouldn't say discovered. Actually, it was discovered by multiple satellites. So we detected 51 gamma ray bursts with that SROS C2 satellite, and that was a major for us within the ISRO uh, scientific community. It was a major achievement because we could actually match our what do you call we could match the time profile of these gamma ray bursts with international satellites of NASA and so on. But then by 1992, the Compton Gamma Ray Observatory, which was launched by NASA, came into functioning, and therefore they had much bigger payload, and they could triangulate with multiple detectors on the same satellite. And so that took over the gamma ray burst field from around 1990, early 1990s. And then after this success, I was part of the mission called the Indian X-ray Astronomy Experiment. In fact, this Indian X-ray Astronomy Experiment was the one which was proposed even before gamma ray burst, but it needed about 50 kg of payload mass. And so because of the early mass constraints, we flew the gamma ray burst experiment first. And when the PSLV became available, we flew the Indian X-ray Astronomy Experiment, which was a collaboration between Tata Institute of Fundamental Research and ISRO. And we built part of the experiment, and they built most of the detectors. And that was a very great success because on the IRS, it flew on IRS P3. The reason it's called IRS P3 is because the satellite itself was a remote sensing satellite. We flew piggyback on it, and we had this constraint that we could not observe the X-ray sources all the year round. When there were monsoon months, when the remote sensing payloads could not operate, we could operate the X-ray experiment to look at the sky. So we had about 3 months a year of observation, but it was a great success because IRS P3 was the first satellite with which we did inertial pointing at specific sources on the sky. Till then, remote sensing was done to look at the Earth, but we never looked at specific sources in the sky. So this was made possible with the star sensors which were there mounted, and we could actually point to individual sources in the sky with arc minute to arc second, arc minute accuracy at that time. Yeah.
And this was still mid 90s.
That was 1996. It was launched, and it was a great success, and we had several PhDs coming out of it. I mean, thesis coming out of that, publications. We had over 25 publications from them, and so on. So it was a great success, first great success for us after the gamma ray burst experiment. So each of them made us go one step at a time. And remember, all these were piggyback experiments. So we made use of the ASLV for gamma ray burst experiment. We made use of the PSLV for IRSP3. After that, we flew a solar spectrometer, which was a which was a collaboration between ISRO and PRL, and that was flown on a geostationary platform, again a piggyback experiment. And then we also had some experiments which were again flown on some international launch satellites and launches. But by then, after the success, see, the major contribution from the Indian astronomy experiment was that we could do science, we could point at individual sources, and therefore that laid the foundation for scientists as a group to come forward and put a proposal to ISRO saying that we need now a dedicated astronomy satellite. Till now we have gone piggyback, but now we are capable of handling this because IXAE was an experiment which was developed in India, and we could do all the software, etc., analysis, and so on. So that was, I could say that was a major step ahead. And based on IXAE, a proposal was made by Professor P.C. Agarwal, who was heading the astronomy group there at PFR, and that we should have a dedicated astronomy satellite. And that laid the foundation for AstroSat, which is short for astronomy satellite, which is now in orbit.
And you had also played a major role in bringing the AstroSat together, and as well as the scientific readings from the spacecraft afterward.
Yeah, so this was a phase of piggyback experiments. After that, this proposal had come. We had started discussions on what should the AstroSat consist of. You see, at that time there was this Chandra observatory, huge observatories which were being flown by NASA. You remember the great observatories. Hubble Space Telescope was already in orbit, and so there was a large discussion amongst the scientific community within India that what could we do when there are these huge, big observatories already launched or getting prepared. So that was when we came up with this idea of a multi-wavelength satellite, and that was proposed. Meanwhile, ISRO itself wanted to go further in technology. And so it was an ISRO proposal that we should go to a lunar orbit. So in parallel, while we were working towards the AstroSat, the payloads were defined, the project was approved in around 2004. In parallel, ISRO initiated the Chandrayaan series with Chandrayaan 1, and that was meant to go into lunar orbit. And so they decided on a few payloads which were going to be developed in-house, and there was also a first time call for payloads from international partners. So Chandrayaan 1 in fact had a good number of payloads built in-house, nationally, and also payloads from other scientific institutions from abroad, both European and American. So that was going in parallel, and we were doing the AstroSat. Most of it was built in-house, but we had a collaboration for two of the experiments. One was the UV imaging telescope that had a collaboration with Canadian Space Agency, and the soft X-ray telescope had a collaboration with University of Leicester in UK. But apart from that, all the other experiments were built in-house. That is the large area X-ray proportional counter, the cadmium zinc telluride imager, and the scanning sky monitor. They were completely built. And AstroSat was the first, satellite which till then we were actually working with Tata Institute of Fundamental Research and Physical Research Laboratory. If you remember, the ISRO itself started with science activities to study the atmosphere with the early launchers, which were launched from Tumba, but they were launchers from NASA. But then, so at that time itself, the rockets used to carry experiments made either from Physical Research Laboratory or Tata Institute of Fundamental Research. Both these groups were involved in X-ray astronomy and also in atmospheric physics. But then when it came to SAT, I started my thing from the satellite part. So AstroSat became the first satellite where we invited proposals from many institutions within the country. So that's how the Indian Institute of Astrophysics took the overall responsibility of building at Bangalore, building the UV imaging telescope. The TFR again built 3 experiments on AstroSat. We built one of the experiments on AstroSat. So it went to Indian Institute of Astrophysics. And then we had other institutions like Inter-University Center for Astronomy and Astrophysics in Pune. They built parts of some of the experiments. Like for the cadmium zinc telluride imager, they were collaborators. For the scanning sky monitor, they were collaborators. They created designs. They did the calibration, etc., etc. Then Raman Research Institute. There was one scientist at Raman Research Institute who did part of the calibration for one of the experiments. So this is how we brought together a collaboration with multiple institutes for the hardware part. But later, when this was supposed to be a major satellite where we could bring in multiple universities and institutions. So when it came to actual observations and science analysis, we have thrown it open internationally. So AstroSat initially, the first year of operation was guaranteed time for the instrument builders. But after that, gradually we increased the amount of percentage which could be proposal driven. So now people send in proposals and based on and it is reviewed by a scientific time allocation committee, which is outside of ISRO, and they approve the proposals and they decide on how the AstroSat should operate and which sources should be observed. And then the data goes back to the proposers directly, and there is a lock-in period of 1 year, after which the data is made open publicly to anybody as an archival data. So this was again one major step which we covered in AstroSat as operating it as a space observatory. And now we are ready for operating the next one, probably Aditya IL1 and maybe even the ExpoSat. Yeah.
Yeah, so in 2015, when AstroSat launched, it was indeed India's first space observatory, and it was really exciting times. Since then, it has consistently provided really good results with constant teams of scientists working on AstroSat data, even till today.
That's right. Yeah. And we already have over 300 publications, and we already have about 25 PhD theses coming out of it, and so on. So great! It's just great to have this, and we have about 1,500 registered users.
Oh, that's wonderful.
Yeah.
And these are users who will apply for time for the observatory and then utilize it.
Yes, analyze the data and publish the science.
So you have been involved in AstroSat pretty heavily, and I know that you
That's
specialize
right.
in gamma rays and X-ray studies. Could you tell us a little bit about what brought you here? How did you grow up? What did you study? And how much of what you studied did you use in ISRO?
Um, uh, okay. See, many students, in fact, ask me, what should we study to get into ISRO? The answer is, you study any of your science subjects or even engineering, because ISRO has a large component of engineering. So I did, as I said, I did my BSc in physics and MSc in physics. I was keen on physics, keener on biology, but I should say I would have become a doctor if I didn't have to do what do you call dissection in biology classes. I did not want to do dissection at all.
Did you have
At that
doctors in
time,
your family as well?
no doctors. But I liked that. But then dissection was essential at that time when I studied. And so I didn't go the biology way, I went the physics way. And then after doing and I particularly liked experimental physics. I like building instruments. I like testing them. I like seeing that they work and then get the science. So that's my, what do you call, passion. So I did a lot of experimental physics in IIT Madras, where we had a free hand at labs. We could actually do whatever experiments we want. Our projects we could do at whatever time we want, whenever we feel like go into the labs, do the experiments. So I learned a little bit, and I also did MSc Physics with electronics. So I learned a little bit of electronics also with that. And that's how I joined ISRO. And I should say one more thing. While we were waiting for these Indian satellites to be flown on Indian launchers, uh, I also got involved in optical astronomy. See,
Oh,
the
wonderful.
advanced, I will tell you the thing behind this. Why X-ray and gamma ray, you might ask? UV, X-ray and gamma rays, at least the lower energy gamma rays, do not pass through the atmosphere of the Earth. So one has to go above the Earth's atmosphere for UV and X-rays, definitely above 120 kilometers. So satellites or rockets become essential for flying UV and X-ray experiments, and also low energy gamma rays experiments. But for optical, radio, etc., you can observe them from ground. So while we were waiting for this, we also decided we should observe some of these objects, because many of these X-ray objects at that time we were studying were X-ray binaries, because they were the bright objects which you could study with a smaller area experiment. Now these X-ray binaries consist of one object which is a compact object called a neutron star or a black hole, so exotic object, but which takes in matter from its companion. And the companion could be studied in optical. Yeah. So we decided to study the optical counterparts of X-ray binaries. It started with that, of course, but then we went on to study white dwarfs. We went on to study cataclysmic variables, etc., white dwarf binaries as well. So I also used to go to optical observatories at Kavalur, Nainital, that is Aries Nainital, now Aries Nainital, that time it was Manora Peak Nainital, and also the Guru Shikhar Observatory at off Pier. So we had several. We also learned the art of publishing, writing papers, etc., which is an essential part of a scientist's life. With that, so that time we also built the country's first two-channel photometer to observe these variable stars. So my interest is to study variable stars, make instruments for them in all these bands. Yeah. So
That
I
sounds
was involved
really nice.
in the making of the gamma ray burst experiment, then partly in the IRS-P3 experiment, and also the scanning sky monitor on AstroSat, and partly involved in the GSAT experiment also. Yeah.
That's lovely. All of that is like high energy physics, all of
Yes.
the ionizing radiation bits that you have been
Yes.
involved in.
Yes.
Apart from AstroSat, you've also been involved in planetary and interplanetary mission, the three Chandrayans, I believe the beginning of Aditya as well, and definitely Mangalyaan. Could you please tell us a little bit about your experiences working on these missions?
Okay. As I told you, while we were doing the AstroSat, Chandrayaan 1 came up. And so our group actually was involved in making two experiments for Chandrayaan, and one of the international collaborations also. So there they were involved in the testing and calibration and so on. And so Chandrayaan 1 gave the exposure for the group to actually collaborate with international partners and also collaborate with other partners as we had done with nationally for developing the indigenous experiments. And so Chandrayaan 1 gave ISRO the big step of going to a planetary system. I mean, one of the systems outside the Earth.
Outside of Earth, yeah.
Yeah. But then, following Chandrayaan 1, Chandrayaan 2, it was decided that we would have not only an orbiter, but also a lander and a rover. So this Chandrayaan 2, which initially started as a Indo-Soviet collaboration at that time, gradually, due to various reasons, the Russian part we had to do it as an Indian, full-fledged Indian mission. And at that time, we proposed for the indigenous lander and indigenous rover, etc. So by that time when Chandrayaan 2 was proposed, I had gone from the satellite center to the headquarters where, as a program director, I have to take care of all experiments, whether I work on it or not. And that's a place where we don't actually work on hardware. We enable the people who work or propose for these experiments to actually come up with those experiments and test them, calibrate them, review them, and so on. So Chandrayaan 2, I was there at when the proposal was approved, and right through when the payloads were developed and so on. So I was in the review process and so on. And then came the next step while we were doing Chandrayaan, the Mars orbiter mission, because technically we have gone to the lunar. We also want to go to another planetary object, because although you went to moon still orbits around the Earth.
Yeah.
So it's still a combined Earth lunar system. Whereas if you have to go to Mars, you have to totally leave the Earth's gravity and get into what is called the heliocentric orbit. And so that was a major step which was achieved in Mars orbiter mission. Of course, you have heard a lot on the technical achievements of the Mars orbiter mission, I suppose, from various people. So the science experiments itself, they again, I should say, again, a very, very severe mass constraint of just 15 kg, and there were 5 experiments. So each of them got only about 3 kg or less. some of them exceeded 3 kg, and so some of them got less than 3 kg. That was a technical challenge for all of them, to make an imager which is compact, at the same time very, very viable in the where many other orbiters were there.
Even if it is not sophisticated and is only a demonstrator.
Yes. No, there was this. See, scientists always want to make it a little sophisticated only.
Yeah.
So how best to do it? How best to do it as a mission was the thing. So we flew this. So that's how we flew this. 3 payloads were developed by the Space Application Center, Ahmedabad, one of which was an imager, which was a modified imager of the Chandrayaan thing. And we made best use of the fact that we had an elliptical orbit around Mars. So this imager could take photographs of Mars as a disk, full Mars.
Yeah.
I mean,
yeah.
So that was greatly appreciated by people who are doing image analysis for Mars as a whole, where you are seeing whether the dust storm initiated somewhere and how it traveled and so on. Amateur astronomers were greatly enamored by this full disk image. And then while the orbit came near, we could actually go to few tens of kilometers resolution. So we had this experience of high resolution at the same time full disk
imaging the full disk. For at least 8 years, I think Mangalyaan was the only spacecraft which could image Mars as a full disk.
That's right, because the other satellites had very high resolution imagers, but they had to create this image out of many mosaics. We could do it with a single snapshot of few hundreds of milliseconds. So that was a major achievement. And then I would say that one was accommodating. And then with the methane was a very, very current topic at that time, to detect methane emission from Mars. Because one is to test whether life exists, whether methane is biological, whether emission, first of all, whether emission is there. Second, whether it's biological or geological and so on. So because we had this mass constraint, we couldn't put a full-fledged spectroscopic experiment. So we decided to actually use the lines of methane, and try to find out whether methane is existing. Again, we knew that this highly elliptical orbit would give us very good detection only when it comes close. But we also wanted to know if the emission is very high, as was thought by some of the ground-based detections. Maybe we could even detect it while we were going to the aperion of the orbit. But then, I should say, we didn't detect. But then, neither did, for example, the rovers on the Mars itself could detect. And so it is thought that maybe it is time dependent, maybe it's very, very transient, the emission, we don't know yet. So we have to see in future whether we can detect methane and we can see whether there is life below the surface and so on and so forth. So as I said, even though we had a mass constraint, we thought of the scientists thought of ways to actually come up with newer ideas. And so that's how the Mars orbiter mission experiments went. Yeah.
And then you were also involved
And
in Chandrayaan 3.
yeah, one more thing when I went to headquarters was we wanted to actually make sure now that we were having science missions as a whole, we wanted to make sure that this data is made available to as many people as possible. So that's how we made sure the software, etc., is available for making this data open for researchers, um, both the lunar, planetary, and science. So that again was made. So first we started with Chandrayaan data, then Mars data, and now we have AstroSat data. So we want all of the science missions, the data to be made open after the payload PIs or the proposer PIs analyze it.
Open
So
source is the way to go. Everyone's doing it
yes,
now.
yes,
Yeah.
because you see, in science, as you know, one scientist doesn't contribute a major thing alone. Everybody grows on what has already been done. And so this data, if it is available, 5 years down the line, when very, very sophisticated instruments come and they are able to do much better, they might at that time want to check whether, even with this course thing, whether there was signature or whether there was a timing which could not match, etc. Right? So that kind of long-term studies is also possible if the data is available open.
Right.
We now want to, in fact, we now want to make some higher level products so that it can, if we want to see if it can also go to students and so on who can make use of images. That's still under discussion. Yeah. And that brought in actually many universities within the country to actually analyze planetary data and science data, because they don't have the wherewithal to make experiments first. Second is, they also don't see, university teachers are mostly tied up with teaching. Some of them do want to do research, but they will not have the time to actually make a proposal. Sometimes they don't have a time to make the proposal, get the time, etc. So now that the data is available, they initially start with analyzing this data. With the confidence they gain with that, they go on to make proposals. So we have got many scientists coming on board like that.
That's really nice. And then I guess going forward, we'll be studying more than just high energy waves and Mars.
Aditya L1, yes. Aditya L1 again got approved. It was originally, it was Aditya. It was a small satellite mission with just one payload, that is the visible emission line coronagraph, VELC. But then, as they designed it, etc., they came to know that the mass would exceed a small satellite platform. So then we had to build a bigger platform. The satellite center had to build a bigger one. Then it was thought that if we are going to make a bigger satellite, why not accommodate more experiments and go further in science? So that's how in around 2013, again, proposals were called for, and then finally we came forward with this suite of 7 experiments, again involving multiple institutions. Now, in fact, Inter-University Center for Astronomy and Astrophysics has now built an complete experiment along with the ISRO for Aditya. So that's how we want to bring on partners, so that it's not just ISRO which makes the complete payloads. We work with them for every one of the payloads. there's a large component of ISRO which is built for them. But we also want to make sure that the scientific teams become enabled to get involved as much in space science as possible. Yeah, so
that makes sense because now ISRO is going to be focusing more and more on interplanetary missions as all the launches become outsourced, and that is the next big frontier for ISRO. It's going to be a really exciting decade, I'm sure.
Yeah, and I also feel that with Gaganyaan, etc., we will, so far we have been doing, as you said, high energy astrophysics and so on. Gaganyaan, we might also get the biologists interested, and we hope that chemists, biologists, etc., will come into our future missions, because that will also throw open what do you call interdisciplinary research overall.
Yeah, and it sounds really promising because after every mission that ISRO launches, it feels like the entire country is tuned in and following, and there is just such an exciting mood in the whole country after a launch.
True. Yeah, that's true. That's one thing I wish to say for women in other organizations where there are small numbers. Women need to grow to higher posts so that the younger women can look up to them and they can ask their doubts. More than looking up to them, actually, they can
be inspired by them.
Not only inspired, be confident to feel that, yes, so-and-so is there, I can also be. See, that's some strength which gets built internally when they work with. So that's how now we have a large number of women pool, and they are holding very, very high posts, project directors, program directors, associate directors, and so on. So I'm looking forward to a day when there will be directors, there will be a woman chairperson of ISRO. In fact, one more thing, I was also a committee chair of the committee to set up a creche for the satellite center. Yes, because we had been raising this, but then finally it was, even the management decided, yes, it is time that we need to set up this creche so that women who work with small children and who don't have the family support could leave their children safely and they could work for. So,
and is this available in all centers right now?
Now, mostly in all centers. I haven't kept track whether every center has this, but yes, there's a lot of this. See, one center starts, then the other center also feels, yes, we need to do this and so on. And especially when they have to work at night because the satellite testing is going on, they can take the children only late. So that also helps.
That's really nice to hear. It's very bright days ahead for ISRO already. Every single mission inspires the whole country. Yes. And we can hope that more and more young people come and join. It's going to be super exciting next couple of decades for sure. Thank you so much, Dr. Seetha. This was really helpful. I learned a lot with our interview. And I hope it's also helpful to our viewers and readers as well. And we wish you a wonderful retirement. Thank you so much for being with us today.
Yeah, thanks so much for you. Thanks so much to you. And I hope post-retirement, I want to see ISRO have experiments on all the wavelengths of the electromagnetic spectrum, and also particles and charged particles and neutral particles and so on. So I hope they just go out on science.
All out in science and research. Yes, I hope so too. I really hope so too.
Yeah.
Thank you so much.
Thank you so much, Sandhya.